The same machines that power 440 nuclear reactors around the world can also build a weapon capable of leveling a city. The difference between fuel and fallout isn't the machine. It's how long you let it spin. Right now, in facilities scattered across a dozen countries, thousands of centrifuges are spinning at 100,000 RPM, pulling apart uranium atoms one neutron at a time. Some of those facilities are powering hospitals, laptops, and electric cars. The science behind what they do is one of the most demanding engineering problems humans have ever solved. But almost nobody understands how it actually works. So today, we're going to look inside the centrifuge halls, the conversion plants, and the atomic structure of uranium itself to answer one question: how do you separate something that's almost identical to itself? Let's start with the rock. If you walk into a uranium mine in northern Canada or central Australia, what you'll see doesn't look special. Yellowish-gray ore mixed in with regular stone. Most of the rock around it is granite or sandstone. The uranium itself is heavy, dense, slightly radioactive, and surprisingly common. There's more uranium in the Earth's crust than silver. Uranium is element 92 on the periodic table, the heaviest naturally occurring element on Earth. Every uranium atom has 92 protons in its nucleus. That number is fixed. If you change the proton count, you have a different element entirely. But the number of neutrons in the nucleus can vary, and this is where things get interesting. There are two main versions of uranium found in nature. The first is uranium-238, which has 92 protons and 146 neutrons. The second is uranium-235, which has 92 protons and 143 neutrons. They are chemically identical. They look the same. They behave the same in almost every situation. The only difference is 3 neutrons. That 3-neutron difference is the entire reason this video exists. When a uranium-235 atom is hit by a slow-moving neutron, something remarkable happens. The nucleus becomes unstable, splits in two, and releases an enormous amount of energy along with 2 or 3 more neutrons. Those neutrons then strike other U-235 atoms, splitting them, releasing more neutrons, and on and on. This is a fission chain reaction, and it's how every nuclear reactor on Earth generates electricity. Uranium-238, despite being almost the same atom, doesn't do this. When a slow neutron hits a U-238 atom, the atom usually just absorbs the neutron and becomes a different element entirely, plutonium. It doesn't split. It doesn't sustain a chain reaction. For the purposes of generating power, U-238 is essentially dead weight. And here's the problem. When you dig uranium out of the ground, you get a mixture of both isotopes, but the ratio is brutal. Roughly 99.3% of every uranium sample on Earth is the useless U-238. Only 0.7% is the useful U-235. You cannot run a commercial nuclear reactor on 0.7% fuel. The chain reaction won't sustain itself. There aren't enough U-235 atoms close together for the neutrons to find them before getting absorbed by something else. To make uranium useful, you need to increase the concentration of U-235 to somewhere between 3 to 5%. That process is called enrichment. So the central question is this: how do you separate two atoms that are chemically identical and differ only in mass by about 1.3%? The answer is one of the most demanding engineering problems humans have ever solved. The first time anyone tried to enrich uranium at industrial scale was during World War II, inside a sprawling facility in eastern Tennessee called Oak Ridge. In 1938, 2 German scientists named Otto Hahn and Lise Meitner had discovered that uranium atoms could be split, releasing energy. By 1942, the United States understood that whoever could enrich enough U-235 first would build the first atomic bomb. The Manhattan Project was born, and Oak Ridge was its industrial heart. The main building at Oak Ridge was called K-25. When it was completed, K-25 was the largest building on Earth by volume. It covered 44 acres. Inside, an army of workers operated a process called gaseous diffusion, which would dominate uranium enrichment for the next 60 years. Gaseous diffusion works on a simple principle. If you turn uranium into a gas and force that gas through a porous barrier, the lighter U-235 molecules will pass through slightly faster than the heavier U-238 molecules. The trouble is, the difference is incredibly small. After one pass through a barrier, the gas on the other side is only about 0.4% more enriched than it was before. To get from 0.7% U-235 to weapons-grade material above 90%, the gas had to pass through thousands of barriers in sequence. Each stage produced a tiny improvement. The full system at K-25 contained more than 3,000 stages, connected in a continuous loop, processing the gas over and over until it finally reached the desired concentration. Producing the gas itself was its own engineering challenge. Uranium metal had to be combined with fluorine to create uranium hexafluoride, a compound that becomes a gas at relatively low temperatures. Uranium hexafluoride is also highly corrosive, reactive with water, and unforgiving to handle. Every pump, pipe, and barrier inside K-25 had to be made from materials that wouldn't degrade in contact with it. The energy demands were staggering. K-25 alone consumed roughly 2,400 megawatts of electricity at peak operation, which was a substantial fraction of the entire electrical output of the United States during the war. New power plants were built specifically to feed the enrichment process. Entire towns were built around it. At its peak, the Manhattan Project employed 130,000 people, and most of them had no idea what they were actually working on. Gaseous diffusion produced the uranium for the bomb dropped on Hiroshima. After the war, it became the standard method for both military and civilian enrichment in the United States, France, and a few other countries. K-25 ran for decades. But gaseous diffusion had a fatal flaw. It was extraordinarily energy-hungry. The electricity required to enrich uranium this way represented a meaningful percentage of the cost of the final fuel. By the 1970s, engineers were already exploring alternatives. One of those alternatives would eventually replace gaseous diffusion almost entirely. That alternative is the gas centrifuge. Imagine a tube, about 6 feet tall and a few inches across, sealed and filled with uranium hexafluoride gas. Now imagine spinning that tube at 100,000 revolutions per minute. The metal at the outer edge of the tube is moving at twice the speed of sound. When you spin a gas at those speeds, something interesting happens. The heavier molecules in the gas are pushed outward by centripetal force more strongly than the lighter molecules. The slightly heavier U-238 molecules concentrate near the outer wall of the tube. The slightly lighter U-235 molecules concentrate closer to the center. It's the same effect as a salad spinner, except instead of separating water from lettuce, you're separating two atoms that differ by 1.3% in mass. And you're doing it at speeds that would tear ordinary materials apart. A single centrifuge, spinning at full speed, produces only a small enrichment of the gas inside it. To get from 0.7% to 5%, you need to connect thousands of centrifuges together in what engineers call a cascade. The slightly enriched gas from one centrifuge gets fed into the next, and the next, and the next. Each stage pushes the concentration up a little further. The engineering inside a single centrifuge is brutal. The rotor has to be perfectly balanced. Any imperfection, any tiny asymmetry, and the centrifuge will tear itself apart in seconds. The materials have to withstand enormous mechanical stress. Modern centrifuge rotors are built from miraging steel, or, more recently, carbon fiber composites. The bearings are often magnetic, suspending the rotor in midair to eliminate friction. The vacuum inside the casing has to be near perfect, because any air resistance at those speeds would cause catastrophic heating. A modern centrifuge enrichment facility looks like a vast warehouse filled with thousands of these tall, slender tubes, all spinning silently. The process is so much more efficient than gaseous diffusion that it consumes roughly 50 times less electricity for the same amount of enriched uranium. Today, almost every country that enriches uranium uses centrifuges. Russia, the European consortium Urenco, China, and several others operate centrifuge facilities at industrial scale. So we've covered the science of why enrichment is necessary, and the engineering of how it actually happens. But to understand the full picture, you have to follow uranium through its complete journey, from the rock in the ground to the fuel rod inside a reactor. It starts at the mine. Uranium ore is dug up and crushed into a fine powder. The powder is then chemically treated, usually with sulfuric acid, to dissolve the uranium out of the surrounding rock. The result is a yellow concentrate called yellowcake, which is uranium oxide. Yellowcake is roughly 80% pure uranium by weight, but it still contains the natural ratio of isotopes. It is not yet enriched. Yellowcake gets shipped to a conversion plant, where it's combined with fluorine to produce uranium hexafluoride. This is the gas form that centrifuges can actually work with. The hexafluoride is sealed into specialized steel cylinders and transported to the enrichment facility. At the enrichment facility, the gas is fed into the centrifuge cascades and slowly enriched up to reactor-grade concentration, somewhere between 3 and 5% U-235. This typically takes weeks of continuous operation. The enriched gas is then drawn off and shipped to a fuel fabrication plant. At the fabrication plant, the uranium hexafluoride is converted back into a solid form, usually uranium dioxide. This solid is pressed into small ceramic pellets, each about the size of a pencil eraser. The pellets are stacked inside long metal tubes called fuel rods, which are made from a zirconium alloy that's transparent to neutrons. The fuel rods are bundled together into fuel assemblies. Those fuel assemblies are what gets loaded into the reactor core. A typical commercial reactor contains hundreds of fuel assemblies, with hundreds of rods each. Once the reactor is running, the U-235 atoms inside those tiny pellets begin splitting, releasing neutrons that split more atoms, generating heat that boils water, that spins turbines, that generate electricity. A single uranium fuel pellet, the size of a pencil eraser, contains as much energy as a ton of coal. Step back for a moment and consider what we just walked through. To turn rocks into electricity, we have to dig up ore, chemically extract the uranium, convert it into a corrosive gas, spin that gas in centrifuges at twice the speed of sound to separate atoms that differ by 3 neutrons, convert it back into a solid, press it into ceramic pellets, stack the pellets into specialized rods, bundle the rods into assemblies, and load the assemblies into a reactor where the chain reaction we described earlier finally produces useful heat. This entire pipeline exists because of that 0.7%. Because nature gave us uranium in the wrong concentration. Because U-235 and U-238 are chemically identical. Because the only thing that distinguishes them is mass. And that mass difference is small enough that separating them required some of the most demanding engineering humans have ever attempted. Today, around 10% of the world's electricity comes from this process. In countries like France, the figure climbs to roughly 70%. The carbon emissions avoided by enriched uranium fuel compared to coal or natural gas are measured in billions of tons over the lifetime of the global reactor fleet. The engineering keeps improving. New centrifuge designs spin faster and more efficiently every decade. Laser enrichment, a method that uses precisely tuned light to selectively excite U-235 atoms, is being developed as a possible next-generation technique. And small modular reactors, which are being deployed for the first time in this decade, will eventually require their own enrichment pipelines. But the core science hasn't changed since 1938. Uranium-235 splits. Uranium-238 doesn't. 3 neutrons separate them. And we've built an entire industry around exploiting that difference. So the next time you flip on a light switch in France, or charge an electric car in Ontario, or read about a new reactor going online in the United Arab Emirates, remember what's happening upstream. Somewhere, a centrifuge is spinning at 100,000 RPM, separating atoms that differ by less than 2% in mass, doing the patient work of turning useless rock into the densest energy source humanity has ever harnessed. That's the science of enrichment. If you want to see how nuclear reactors actually use that fuel to generate electricity, the breakdown of reactor design is on screen now. Click it.